Where are you from, Jyoti? You are from India or you are from outside the India? Is it morning for you? Okay, good evening. Fine. Okay, not an issue. Not an issue, Jyoti. I thought you are from outside the country. Okay. So I have only 11 students. So can you all inform to your friends? Okay, you're from Delhi. Good, good. Can you all inform to your friends, guys? So now we are very close to 5:50. So it is the right time to start our session. Good evening, Yesh. Guys, actually, today we are conducting fourth session, but still we have not yet started with the second session concept. Correct, no? Yes, today what I'm going to do, so I'm going to start with the second session concept. So if time permit, I will start with third session concept. Maybe this week, I'm planning to take extra class, guys. You people told, right, Saturday evening you'll be free. Shall I take one extra class on Saturday evening? Saturday evening is okay for you all, guys. Okay, Saturday evening means at what time? What is the comfortable time for you people? What time is comfortable for you all, guys? 7 to 9? Okay, same time. Then 6 to 8. 6 to 8 is okay for you? 3 to 5. Okay, I have to check with 3 to 5. But for me, 6 to 8 or 7 to 9 is okay. No issue with 6 to 8, right? Okay, guys, I will try to take one extra class. Since we are lacking in 2 sessions concept, I have to take one more extra class. Before your mid-semester, I will take one more extra class, guys. So is it okay for you all? So in Bangalore, it is continuous raining, guys. Since morning, it is continuously raining. So even in Hyderabad, same situation. Okay, in Delhi also. Oh, maybe throughout India, this is the same situation we are all facing. Okay, guys, now we are close to 5:50. Let me start with today's session. I think my screen is visible to everyone, right? So can you all quickly confirm my screen is visible? Yes. Okay, fine. Thank you, guys. Yes, guys, without wasting time, let us start with today's session concept. Guys, actually, yes, once again, welcome back, guys. Welcome back, everyone, to our third and no, this is not third session. This is the fourth session, but still, I'm talking about session 2 concept. I'm really excited to see you all in today's session, guys. And before we dive into today's topic, let's start with a quick thought. Okay, so I always used to give one quick thought. So based on today's topic, guys, this is the thought I have taken from what? One of the famous person. The future belongs to those who learn more skills and combine them in a creative ways. So this is exactly what we are doing here. We are not just learning about big data, so but we are also understanding the foundational principles that makes it possible. Guys, so by the end of this course, so you'll be able to combine these skills in some truly creative ways to solve real world problems. Okay, so yes, you all know, right? In our last session, we touched upon the basics. So setting the stage for what's to come. And today we are going to get into the heart of parallel and distributed computing. So this is the concept we have planned to complete today. So this is the bedrock upon which all big data technologies are built. Okay, understanding these core concept is not just important, guys. It is essential. Okay, so all right, guys. So let's start with the very first topic, guys. What you can see here, what you can see here, guys. Hmm? See, now you might be wondering, right, why we are starting with this topic when the course is about big data. So this is a crucial point, guys. So it is highlighted right here. Okay, the core principle is that big data system use the fundamental concept of parallel and distributed computing. Okay, we cannot build a house without strong foundation. So for big data, so this is our foundation. Remember this. So this is foundation. So let's move on and look at what we are covering in today's session. So this is the slide. Guys, in today's session, so we'll quickly go through the parallel concept. Okay, first we start with a formal definition of what parallel and what distributed systems are. And so we have all heard these terms, but it is important to understand the precise difference and how they relate to each other. Okay, next to that, so we will be diving into motivations behind using these systems. So why do we even bother with all this complexity? And why cannot we just use a single powerful computer? So we explore the reasons from technological limitations to the inherent nature of certain problems. Then we will discuss something called limits of parallelism. So this is a very important concept. Just because we add more processor does not mean our program will get infinitely faster. Okay, there are real mathematical limits to the speed up we can achieve. So we will be looking at some key laws that govern this. After that, we will compare two major approaches for how these systems handle data and communication. Okay, that is shared versus message passing. Okay, so this is a fundamental architecture decision with huge implications for how we write our programs. Okay, following this, so we'll get into the different data access strategies. So how do we manage data across multiple machines? And we will discuss techniques like replications, partitions, and messaging. Okay, so you will see these terms again and again in the context of big data systems like Hadoop and MongoDB concept. And finally, guys, we will wrap up by talking about cluster computing. Okay, what is a cluster and how is it different from single computer? And why is it the go-to architecture for almost all modern big data workloads? Okay, so as you can see here, so we have packed and very foundational agenda. Okay, let's start with the basic by first understanding what serial computing is and which is the opposite of what we want to achieve. Okay, so let me check once whether you all ready for today's session. You all ready, guys? Can I get quick RADY and chat box? RADY and chat box. You all ready for today's session with high energy, guys? I want you people to show always energy in the evening. It is like coffee for me. Yes, thank you all, guys. Now, can anyone tell me what is serial computing? What do you mean by serial computing, guys? What do you mean by serial computing? Okay, instructions are processed sequentially. Very good answer. Very good answer by Arup. So give me a big round of applause, guys. So I got very quick response from Arup Jyoti. Correct, no? Yes, guys. To truly appreciate the power of parallel distributed system, we first need to understand the traditional way of computing. So which is called as serial computing. I got one more reply from Tanya. So instructions are executed one after another in a single sequence. So typically on a single processor. Very good answer, Tanya. Okay, so this is what I have been doing with our personal computer for a long time. Correct now? This is what we are doing with the personal computer for a long time. So what it is, guys? So as your friends told, in serial computing, a problem is broken down into, see, with diagrammatic, I'm going to show you this. So this is, your problem is broken down into discrete series of instructions. So think of it like a recipe. So you have a list of steps. You must follow them in order. Guys, these instructions are executed one after another sequentially. Look at here. It is executing in sequential order. So there is no multitasking at the instruction level. Remember this. So it is a single fine line, one instruction waiting for the previous one to finish. Correct, no? So this all happens on a single processor. Look at here. We have only one processor here. Only one instructions can be executed at any given moment of time. So it will take only one instruction and it will execute this. The processor is like a single chef in a kitchen. And no matter how skilled they are, and they can only do one task at a time. That's it. Nothing else, guys. Then what is the key characteristic of this model? Guys, the key characteristic of this model is the use of single data store. Correct? Now you can observe here. See here, we have only one storage device. We have single data store. The meaning of this is only one memory and one disk. That's it. Okay, this is a simple and straightforward model, guys, but it has some serious limitations, especially when dealing with massive amount of data. Guys, this traditional architecture is often referred to as a von Neumann architecture. This architecture is called as von Neumann architecture. See here, I clearly mentioned. Okay, so which has a common memory store and common pathway for both instructions and data. So instructions and data are going to move in the same line. So this can cause performance bottleneck. Okay, that performance bottleneck is called as von Neumann bottleneck. So which is why modern architectures are separate caches. Modern computers are using separate caches. Correct? No. For instructions and data to reduce this problem. That architecture is called as Harvard architecture. This Harvard architecture is containing separate memory for data and separate memory for instruction. Understanding my point, guys? So this is one big bottleneck with respect to single storage system. Now, what if we could get more than one chef working in our kitchen? So that is where parallel computing comes in. Okay, let's move to the next slide and explore it. Okay, so now I'm talking about parallel computing. Look at here, guys. So now we have understood serial computing. So let's talk about its opposite and the first major step towards big data system, that is called as parallel computing. Guys, we all know, right, the definition of parallel computing. So parallel computing is all about using multiple compute resources simultaneously to solve computational problems. So instead of one chef, we now have many chefs in our kitchen. So all working at the what same time. See, look at here. So here we have separate processor. Here we have separate processor. We have totally four processors here. All four processors are working in parallel in a given time. Correct? No. Guys, the computational problem. See, this is computational problem. So this problem is broken down into discrete part that can be what solved concurrently. Look at here. So this is having separate pieces. This is having separate pieces. So all four are working concurrently here. This is a critical step, guys. If a problem cannot be broken down into independent parts, then it cannot be parallelized effectively. See, for example, calculating the sum of numbers from 1 to 100. Okay, you have started what calculating the numbers from 1 to 100. So this can be parallelized, right? But a problem where the output of each step is the input to the next cannot be. So each of these part is broken down further into its own series of instructions. Okay, here clearly I've mentioned all the points, guys. You can go through this later. Okay, these instructions from each part then executed simultaneously on a different processors. And this is the core of parallel execution. So that is nothing but what? Multiple things happening at once. That is called as parallel processing. Hope this is clear to everyone. Guys, in this model, so different processor can work with independent memory and storage. So this could be containing independent memory and storage. Separate one. So here also, memory and storage. Storage is nothing but a hard disk, guys. Okay, both are not same here. This is a different from single memory store. And finally, there has to be what? An overall control or coordination mechanism to manage these different parts and combine the result at the end. Okay, so this is where the complexity comes in, but it is also where the power lies, guys. So parallel computing is a huge leap from serial computing. But how parallel can we get, guys? Correct? No, how parallel can we get? So now next onwards, we are going to what? Look at the next slide to see spectrum of parallelism. So from very simple to very complex methodology. Okay, so now look at here. Look at the slide I'm explaining you all. Guys, this slide is a very helpful way to visualize the different level of parallelism from the most granular to the most distributed. Okay, think of it as a what spectrum with more coupling and more granularity of parallelism as we move from left to right. Okay, I'm moving from left to right, guys. I'm starting from here and moving towards right. See, on the left side, so we have what we have here, guys. So we have pipelining. Correct, no? Or you can see here pseudo parallel intra-processor. So this includes techniques like pipelining and superscalar execution. Look at here. So here it is including two, pipelining and superscalar execution. Guys, in pipelining, a processor starts on a new instruction before the previous one is fully finished. So think of a what factory assembly line where multiple cars are being worked on at different stages simultaneously. What in case of superscalar? Guys, superscalar is about having multiple execution unit within a single processor to execute multiple instructions at once. Guys, these are very fine grained. Okay, these are very fine grained. So instruction level forms of parallelism. See here clearly I mentioned. Guys, moving to the right. So what do we have here on right hand side? See, moving to the right, we have parallel. Correct? No, parallel domain. Okay, so which are common in our laptops and desktop today. So have multiple independent CPUs on a single chip. Correct? No. So suppose I'm asking you to say, so what is your computer configuration? Means usually it will be having what? More than one core. So you'll be having dual core system, quad core system. Okay, I'm asking you about your desktop means that is also in the same case, right? The meaning of this is, so each and every computers nowadays will be having multiple independent CPUs on a single chip. And also you can observe here. So we have a concept of shared memory or a shared memory system. This shared memory system allow different processor to access a common memory space via interconnection concept. So this level of parallelism is often at the task or data level. I've clearly mentioned here. This is at task level or at the data level. Remember this. The coupling is tight because the processor are physically close and often share a memory bus. So further moving to the right, so we have a distributed concept here. Okay, distributed space. So this includes system that use message passing over an interconnection. Look at here, message passing over interconnection. Correct? No. So like your cluster machine, your grid concept, your cloud concept, everything is going to use this distributed concept. So in this case, the processor do not share a common memory. They communicate by sending messages to each other over a network. So the granularity is coarser here. Granularity is coarser here. So often at the application or service level. See here, task level, data level, application level, and also service level, it is what? It is very close actually. The coupling is much looser since the machine can be physically far apart. Guys, this spectrum is very important to understand. So as it shows how we are progressed from simple single processor improvements to complex large scale systems. The technology we use in big data like Hadoop, Spark, so fall squarely in distributed and parallel parts of this spectrum. Okay, so here the complete big data concept is belongs to this or it belongs to distributed concept. I think till here everything is clear to each and everyone. Shall I get quick confirmation on chat box? So till here everything is clear, guys. Till here everything is crystal clear. Shall I get quick confirmation from each and everyone? Clear? Okay, fine. So next look at here, guys. Next I'm talking about distributed computing. Let us start with the distributed computing because distributed computing is a fundamental concept with big data concept. What is distributed computing? That is the first question. Guys, building on what we have just discussed, in a distributed system, multiple computing resources are connected in a network. You can observe in the diagram. Okay, and computing tasks are spread across these resources. See, look at here. Look at the diagram. Then what is the goal here? The goal here is not just to run things at the same time, but to leverage a network of independent computers to work together. So this approach leads to an increase in a speed and efficiency of the system. See, I mentioned everything in a second point. Correct? No, these systems are often faster and more efficient than traditional methods of computing. Correct? No? Guys, a key advantage is their suitability for processing huge amount of data in a limited time. So think about a large e-commerce website on a holiday sale. So it retrieves millions of requests at once. No single server can handle this. So, but a distributed system with a network of servers can share load and process all those requests simultaneously. So this is where distributed computing really shines, guys. Okay, you can observe in this diagram, I have mentioned each and everything. Okay, it is a conceptual diagram of distributed system. So you have control node here. You can observe. So you have a control node separately. So this control node is connecting with different servers. So this is connected with web server. You can observe here. Somewhere I have mentioned web server. So this is connected with Exchange server. This is connected with CRM server. So as well as sometime it is going to connect with the desktop systems. Sometime it is going to connect with laptops. Sometime it is going to connect with normal system by using internet concept. So we can connect with independent machines together here. Okay, so you can see that there are various machines. So all machines are called as nodes here. All machines are called as nodes here. So each with its own memory and CPU, correct? No. So all connected via network concept. So this is a fundamentally different from a single machine with a multiple processor sharing a single memory space. Okay. So moving to the next slide, you can observe here. Now I'm talking about UMA and NUMA. Maybe you have heard about UMA. So now we are more talking about NUMA versus UMA. Okay, so let me start with the very first one. That is UMA. Guys, this is explaining the key distinctions in the architecture of multiprocessor system, particularly related to how memory is accessed. So we have two main types here, guys. So one is called as UMA, another one is called as NUMA. NUMA I'm going to explain you in the next slide. Okay, let's start with the very first concept that is called as UMA. Uniform Memory Access Multiprocessor. That is the full form of UMA. Clear? So you can observe in this diagram, in a UMA multiprocessor system, all processors share single, see, look at here, all processors share single uniform memory address spaces. See, here we have a memory? Uniform memory address space. This means that this means that the time it takes for any processor to access any memory location is the same or uniform. It is like having a single big library where all the books are equally accessible to all the readers. And these systems typically don't have a common clock. Remember this. So this could be not having any common clock. Okay, so but they use a fast interconnect to connect the processor and memory. So this is a form of shared memory architecture. This is a form of shared memory architecture. Try to remember this. Shared memory architecture. Guys, let's look at the second one. That is called as NUMA. So what is the full form of NUMA? Non-uniform memory access multi-computer. So that is showing in this diagram, guys. That is completely showing in this diagram. Guys, in NUMA multi-computer, see, multi-computer, I'm calling it as multi-computer. So memory access time depends on the memory locations relative to the processor. So it is not uniform. Remember this. So it is like having multiple small libraries So each with a group of readers. A reader can access book for their local library very quickly, but it takes longer to get a book from a different and remoted libraries. Correct? No. See, here locally we have a memory. Accessing this memory is very easy. So once this processor is trying to access this memory, then it is difficult. So these systems may have what? Shared address spaces. Here also we'll be having shared memory, shared address spaces, but they typically rely on message passing concept. Message passing concept. So why message passing concept is required here? Suppose one processor has to communicate with another processor, miss. So then we are going to use a message passing concept here. Understanding my point, guys? Like Yuma, they also don't have a common clock here. So here also there is no concept of common clock actually. Now, can you all tell me what are the differences between Yuma and Yuma? What are the differences between Yuma and Yuma? Can anyone tell me now? See, why we are going to use clock, Ajit? So clock we are going to use for the synchronization purpose, right? So we are not going to use clock here. No common clock we are going to use here. See, common clock we are using means it is going to synchronize each and every task actually. That we are not using here. That is the meaning of no clock, no common clock. Is this clear, Ajit? Ajit, is this clear? Can you quickly confirm? Yes. Now I'm asking you all guys, what are the differences between Yuma and Yuma? So can you please explain about a system having multiple cores in a single processor versus having multiple independent processors? This is what I'm showing, right? See, multiple cores, yes, multiple cores means, suppose we have a multiple cores means then what we have to do, guys? We have to use a multi-threading concept. So internally we can perform what? Parallel computing actually. That is in case of multi-core system. But in case of multiple independent processor means each processor will be having what? Separate memory. That is what I'm showing you in Yuma and Yuma. Okay. So the main difference between Yuma and Yuma is the memory access time, right? Am I right or wrong, guys? The main difference between these two is, what is the main difference, guys? The main difference is, let me write here, memory access time. So Yuma is a simple program because all memory is equally accessible. But it is hard to scale to very large number of processor because the shared bus can become a bottleneck here. But in case of Numa, not like that, guys. Numa scales better because so it can reduce the traffic on a main interconnect by encouraging processor to use their local memory. It is using local memory. So this distinction is very much crucial, guys. So especially when we discuss programming models, a Yuma is like a what? A great fit for a shared memory programming model. While Numa is like a what? Natural fit for message passing. Remember this. Okay. So now let's quickly look at the different kinds of interconnection network that enable communications between these components. Okay. So what are the different methods, guys? What are the different methods we have to discuss now? Huh? Okay. See, look at here. So this is interconnection network. So we have two here. So one is represented by using A, another one is represented by using B. You all look at here, guys. So guys, this slide is showing you two examples of interconnection network that are used to connect processor and memory in these parallel and distributed systems. The efficiency and speed of this network are critical for system performance. Correct? No? So on the left hand side, you just look at here. On the left hand side, we have diagram A. So in diagram A, we are using crossbar switch. So think of this as a what? Very organized and dedicated network of highways. So every processor has its own dedicated, look at here. Every processor has its own dedicated line to every memory bank. Correct? No? Dedicated line to what? Every memory bank actually. This means that a processor can talk to any memory bank at the same time as another processor is talking to the different memory bank without any conflict. So this makes a crossbar switch very fast. That's why I mentioned here. So very fast and highly parallel. So however, it is also very expensive because so as you add more processors and memory units, the number of connections grow quadratically. Correct? No. Quadratically, it is going to what? Grow the number of switches. See, here we have 4 processor and 4 memory. How many switches we have here? How many cross point switches we have here? Suppose you are increasing the number of processor and number of memory means, so this number is gradually increases. That's why I mentioned quadratically it is going to increase the number of what connections. Okay, so I can say n square. So which is scalable for what? Very large numbers. See on the right hand side, look at here. On the right hand side, so we have omega switching network. This is called as omega switching network. This network is designed to be more cost effective. So instead of direct connect from every processor to every memory bank, it uses series of smaller switches. Series of smaller switches we are going to use here. Are you getting my point, guys? See what switches we have used here. 2 cross 2 switch we have used here. Okay, this is used to what? Route the messages. This is mainly used to route the messages. So this is a cheaper to build than a crossbar switch because the number of connection is much lower here. Okay. However, it can be slower because a message might need to go through multiple switches. This is little bit slower compared to the what cross point switch, but number of switches are reduced here. So it can be what slower. I've told you, right? It can be slower because we are using, we have to what go through number of what switches here. And there can be what contention if multiple processor try to access the same switch at the same time. There is a problem of contention here. The choice of interconnection network is a trade-off, guys. Trade-off between speed and cost. Correct? No. So it is a key design consideration for building parallel and distributed systems. Okay. So next we are moving forward and we are talking about instruction stream and data stream. Guys, these are the famous classification of all these different types of architecture. So instruction stream and also data stream. Okay, so what you will remember, guys, once I'm talking about instruction stream and mainstream, what you will remember? So how many of them heard about, okay, this interconnection network is for distributed system. Just now I've conveyed, Priyanka. See, by looking at diagram, you will understand, right? I don't know why you people are asking very basic questions. Look at here, guys. What is processor means? So processor is nothing but a single node, is it? Processor are nothing but a single node here. Ajit, hope you have understood now. Priyanka, it is for distributed computing. So I told you right at the end. See here, I've told you right. So we have to go with these two constraints. Once we are using with distributed computing, so speed and cost both are the constraints, but both we are going to use for distributed computing. Is this clear to everyone, guys? No, why you people see, Ajit, I'm talking about processor. I'm not talking about cores. See, any processor can contain n number of cores, right? So once I'm talking about cores, see, cores are comes in the what implementation implementation actually. So when we are going to consider cores, we are going to consider cores at the time of implementation. Now I am talking about what processor. See, each processor can contain n number of cores. So why you are thinking about cores? I'm not getting your point, guys. See, core is a part of processor. I'm talking about processor now. See, when you're going to write a program, then we'll think about what number of cores. See, for example, you are using Java language. Then you can use the what concept of multi-threading. So there, each thread is going to what? Executed by using single core. Which process takes the priority in Omega switch assignment? That you people have to answer. Joshi. Can anyone answer to the Joshi question? Okay, time is running. Guys, actually, you should be what good at networking concept, guys. Then only you will understand each and every concept in detail. Okay, now I'm brushing up. That's it. I am not going in depth and teaching you what networking concept. Correct? No. Okay. Yes, many of your friends are giving right answers. You just go to that, Joshi. Okay, now I'm moving forward. I'm talking about next slide. Guys, before we jump into Flynn's taxonomy, maybe you have heard about Flynn's taxonomy in your engineering. So which is the what key concept? Guys, we need to understand two basic terms. One is called as instruction stream. Another one is called as data stream. So you have to listen to me carefully now. See here in both we have used the key term stream. Okay, stream is the term we have used in the both actually. Okay, so the term stream here just refers to the sequence or flow. That's it. So this is referred to the sequence or flow. That's all, guys. Okay, guys, you look at here. An instruction stream is the flow of instructions from the memory to the CPU that need to be what executed. In a simple serial processor, there is one instruction stream, but in parallel stream, there could be what multiple instruction stream being executed simultaneously. Just now you people were asking about this, right? See, once I'm talking about single processor, okay, there is a what? Chance of serial executions, serial instructions of stream you are going to get there. But in case of parallel system, there could be multiple instruction stream being executed simultaneously. That is in case of what multi-core system. Try to understand this. Now I think you people are getting some idea. Next, let me talk about data stream. What is data stream? Guys, a data stream is the flow of operands or flow of data. So between the processor and the memory. So here in this case, we are talking about instructions. So in this case, we are talking about data. So data can be operand, data can be data, whatever it is. So this flow can be bidirectional. See, look at here. You can see here, data stream can be bidirectional. But instruction stream is not a bidirectional, correct? No. So as the processor reads data and also writes the result back to the memory. Why it is bidirectional? See, this is taking data from the memory and it is going to perform some computation. After performing computation, it will produce with result. So this result again come back to the memory location. In a serial system, there is one data stream, that's it. But in parallel system, we might have multiple data streams. Guys, understanding these two streams is essential because they form the basis for classifying computer architecture using Flint's taxonomy. So next slide, I'm going to explain you about Flint's taxonomy. Okay, so which we will discuss in the next coming slides, guys. So this classification helps us to categorize and understand different types of parallel systems. So if you have any question on this, you can ask me, guys. So without what I was not looking at your chat box. So now I came back to your chat box and I'm looking at your chat box. Any doubts? So have you all understood what is instruction stream? So what you'll be having in single stream, what you'll be having in multiple stream. So in single stream, instruction is also single. In multiple stream, instructions are parallel. Okay, so you'll be having more number of instructions. Same in case of data also. In data stream also same case. Clear? Okay, now moving forward. Look at here, guys. Next slide, I'm completely explaining on Flint's taxonomy. My dear student, this is a very important slide and a fundamental concept in computer architecture. So make a note of this, guys. This is very, very important. Maybe yes, in your engineering, you have learned this Flint's taxonomy. Guys, this Flint's taxonomy classifies computer architecture based on the number of instruction stream and number of data stream they can handle simultaneously. We are considering both. So let's break down the 4 categories. What is the first one, guys? First one is SISD. Can anyone tell me the full form of SISD? Now easily you can answer to this question. What is SISD? Sir, one basic question. How does a multiprocessor system decide to process instructions sequentially or parallelly? See, that is comes in programming part. Man, why you are asking that question now? See, now I'm giving you only the flavor. That's it. I'm giving you the outer layer of the each and every explanation. Correct? Now, why you're thinking about how it is going to execute. In future, you're going to learn on that. No need to worry now. Single instruction, single data. Correct? No, that is called as SISD. Very good answer. I got quick responses from all. So SISD is nothing but single instruction, single data. This is our classical serial computer or uniprocessor concept. Guys, it has a what? Single instruction stream and single data stream. This is the model of computing we discussed earlier. Pipelining can be seen as an extension here, as it is still fundamentally a single instruction stream, but with overlapped executions. Correct? No? Overlapped executions. So how many of them are aware of pipelining concept? You all aware of pipelining concept? Can you all quickly respond in chat box? What do you mean by pipelining concept, guys? If I start asking questions, you people will take time to answer. So Pipelining. So there is a chance of what? Overlapping of executions, right? In case of pipelining. Yes, sir. Once I'm trying to what? Execute multiple instructions simultaneously, there is a chance of overlapping. So maybe you have learned about data hazard, branch hazard, structural hazard, everything in pipelining concept, right? So that we are going to use in. Okay, yes. Okay, fine. Now look at here, guys. You can observe. So here we have mentioned single data and also single processor, single instruction. That is called as what? SISD. Next, we are talking about SIMD. See, look at here. SIMD means single instruction, multiple data. Okay, single instruction and multiple data. Okay, so in this model, a single instruction stream is executed on multiple data stream. This is like telling a group of people to all add 5 to their own number. So they're all performing the same instructions on different pieces of data, right? See, suppose I'm asking this person roll number is 20. This person roll number is 22. This person roll number is 32. This person roll number is 1 or 2. See, I'm asking each and everyone to add 5 with your roll number means. So each and every one will be having what? Different data, is it? Instruction is same. What is the instruction I'm passing here? I'm passing instruction add 5. But I'm performing this instruction, this what? Addition on different data available on your computer. Correct? No, this is called as single instruction, multiple data concept. So this architecture is very effective for scientific computing and tasks like matrix multiplications, matrix manipulations. Okay, think of GPU, guys. Think of GPU. Okay, graphic processing unit. So which are great for this kind of work, no? So they are tightly coupled system, is it? That is one of the what best example for this SIMD concept. So then what do we have, guys? Third one, we have multiple instruction and single data. So this is the least common type of architecture. So here, multiple instruction streams operate on a single data. Look at the diagram. So this is primarily used for what, guys? This is primarily used for fault tolerance. Correct? No. This is mainly used for fault tolerance. Correct? No. So where redundant processor execute the same task to check for an errors. See, for example, in a spacecraft, so 3 processors might compute the same flight path. And if one's result is different, the other 2 can outvote it. Correct? No? Other 2 are outvoted, right? That is called as MIST concept. And what is the last one? The last concept is called as MIMD. Multiple instruction, multiple data. So this is the most general and flexible category. So it involves multiple instruction streams operating on multiple data streams. So this is the foundation for multi-computers and distributed computing. So almost all modern parallel and distributed systems, including multi-core processors, clusters, clouds, fall into this category. So they are typically loosely coupled, guys. So these are typically loosely coupled. Okay, so with no shared memory concept, remember this. Okay, guys, the diagram on, see, right hand side, we have given each and every diagram. So this is summary of what? 4 categories actually. So it is a fundamental concept that you will use to classify different types of systems throughout your career. So hope everyone see Flint's algorithm. See this and all already you have learned in the bachelor degree, but still I'm explaining you guys. Still I'm explaining you. So if you want more information on that, you go back to your degree and you learn that concept again. So I'm just giving you what is required for my distributed computing concept. What is required for my big data system. That's it. So now hope you all understood, right? What architecture we have used in big data systems, guys. Out of 4, which architecture we have used in big data systems? Can anyone tell me? MIMD? Correct, no? That is what I required. That's it at the end. Okay, now moving forward. Okay, 1 second, guys. Now moving forward, look at here, guys. Some of the basic concept I'm teaching you here. Okay, so this is especially important when we talk about programming for big data system. That's why I'm explaining you here. So here, first let's talk about coupling. So now I'm talking about coupling concept. So this refers to how tightly connected the components of a systems are. So we have two main types. So one is called as tightly coupled, another one is called as loosely coupled. Correct? No. Tight coupling means this is where components like processor share a memory space and are closely linked. Example for this is SIMD and also MISD. Shared memory systems. Communication is very fast in case of what these two tightly coupled concept. So memory are very close to each and every processor here. That's why it is called as tightly coupled. What do you mean by loosely coupled? Guys, this is where systems are connected via network. Correct? No, and do not share memory here. So distributed systems and networks of workstations fall into this category. I've clearly mentioned here. And one more thing, which is slower but allows for greater scalability. See, there is a disadvantage with respect to loosely coupled, but still we have to understand what is important here. Scalability is important here. That's why maximum time we are going with what loosely coupled systems actually. So this tightly coupled system, we are going to talk with respect to memory and also with respect to processor. What is the next concept we have to discuss here? Next, we have to discuss about speed up, which is the key metrics for evaluating parallel programming. So it is defined as the time it takes for programs to run on a single processor. Correct? No? Yes or no, guys? See, look at here, everyone, each and everyone look at here. So T of 1 we have taken. T of 1. So this divided by the time it takes to run n processor. T of n. So we will be studying Amdahl's law and one more, Gustafson's law, to understand the theoretical limits of these speedups. That I will explain in the next coming slide. No need to worry now. So after that, we have one more concept that is called as parallelism of the program. Guys, this is measure of how much of a program time is spent on computation compared to the time spent on communication. Okay, a highly parallel program spends most of its time in computing, not in communicating. That is the meaning of parallelism of a program. And we have finally one more term here, guys, that is called as granularity. Maybe you have heard about this term, granularity. So this is the average number of compute instruction that are executed before communication is needed across processor. So this is a crucial concept. So if you have granularity, the meaning of this is, see here I've mentioned here. If you have granularity, the meaning of this is a lot of computations happens before communication. Then a distributed system is a good fit here. So if we have fine granularity, so we have one more granularity that is called as fine granularity. If we have fine granularity with a frequent communication, then a tightly coupled multiprocess system is better. A small granularity can lead to high overheads and low speed up. So even if a program has high potential for parallelism, this is the overhead we are going to face here, guys. So remember these terms: coupling, speed up, parallelism, granularity. So they are the vocabulary we will use to describe the systems and programs we build. Okay, let's now formally compare parallel and distributed computing. Okay, now formally we are going to compare parallel and distributed computing. So both are not same, guys. Till here everything is clear. Till here everything is clear. Okay, fine. Okay, now look at here, guys. So this is the comparison between parallel and also distributed computing. Guys, we all know, right? Distributed system we have mentioned here and parallel system we have mentioned here. Distributed system is a collection of independent autonomous systems connected in a network with each accomplishing specific task. That is the first point I have mentioned here. Correct, no? And coordination. Next point I'm talking about coordination. Coordination is possible between connected computers with own memory and CPU. Okay. And these systems have loosely coupled and their programs often have coarse-grained parallelism. See, everything I've explained in the previous slide. The same thing I'm explaining here, guys. I'm not explaining you anything extra. The meaning of this is that the tasks are large enough that the communication overhead is small fraction of total execution time. So even I have listed parallel system also on the right hand side. So in a single computer system with several processing unit, one of my friend was asking this question. Single computer system with a several processing unit attached to this parallel system. Okay, so these processing units can all directly access a common shared memory. Okay, so this is a classic example of tightly coupling system. Correct, no? The resources are used to solve a single complex problem in the case of parallel computing. Sorry, parallel systems. The programs running on these systems may demand fine-grained parallelism, where communications happens much more frequently here. So think of this way, guys. Distributed system is like a team of colleagues working in a different offices. So communicating via email and phone. That is called as distributed computing. Then what about parallel computing? Parallel system is like a team of people working in the same room, passing notes and talking directly. So both can be very effective, but they are suited for different kinds of problem and architecture. Only when you are going to take a problem. So based on your problem, you are going to decide whether you have to go for distributed computing or you have to go for parallel computing. So this distinction is important because it directly influences how we design and build our big data system. Clear, guys? So hope till here everything is clear. Till here everything is clear. Have you all understood? So one of my friend was asking the question, multi-core. Same thing I'm explaining you here. Ajit. So is point number 2 in distributed system talking about communication here? Which point you are talking about? Coordination. Coordination is possible between these two connected computers. Yes, that is nothing but a communication only. Message passing. Yes, exactly correct. Yes, exactly correct. That concept I will cover you in the next coming slide. So wait for a while. I'm going to cover that concept also. Okay, fine. Guys, I think till here everything is clear. Guys, the motivation for parallel computing. Now there is a what motivation for parallel computing. What is the motivation? See, look at each and every point, guys. See, guys, let's get into the why concept. So why do we bother with the complexity of parallel and distributed system? So this slide is going to explain each and every concept. I think I have taken 2 slides to explain the same concept. So quickly, I will go through each and every one, guys. First, we have inherently distributed applications. Guys, some problems are just naturally distributed. Okay, a great example is a financial transaction involving 2 or more parties. Correct? No? The transaction involves multiple banks, multiple ledgers, and systems that must all communicate to complete the task. That is the one thing is motivational for us to what? Go with parallel or distributed system. And what is the second point? The second one is create multiple smaller parallel tasks instead of complex tasks. Guys, imagine you need to what? Evaluate and aggregate over 6 months of sales data. This is the real-time example I'm taking you to what? Explain each and every concept. So instead of having one program process all the data, you can have 6 programs, right? And each processing 1 month's data and then combine the result. This is much more manageable and efficient. I'm giving you all the motivations now. And what is the third motivation? Third motivation is related to economics and technology are in our favor. Nowadays, yes, guys, we have entered into economy also. We have entered into technology also. Correct? No. See what I mentioned here. Processors getting cheaper and networks faster. While processor speed have been doubling approximately every 1.5 years, network traffic has been doubling every year. Correct? No. However, processors are also limited by energy consumption. So this shift in cost and performance makes it more economical to use a network of many cheaper processors rather than one very expensive super fast one. I think everyone will agree with my point. Then what fourth one we have to achieve here? Guys, we can achieve better scale using replications or partitions of storage. So think of replicated media servers. So like what Netflix uses for faster access. Or think of how search engines use shard concept or partition concept to store parts of their index. So this allows us to handle more data and more users. This is another motivation. And what is the next one? That is the fifth one. These systems, see, this is provided by the system. Access to shared remote resources, like a what? Central database. This is a kind of what? Central remote databases we are going to use here. And the sixth one, we have increased performance to cost ratio compared to what? Special parallel systems. So you can build a powerful search engine that runs on a network of workstation. Network of workstation, in short form, we are going to call it as now. So which is far cheaper than buying a what? Specialized supercomputer. Correct? No? Yes or no, guys? So as you can see, there are many compelling reasons to what? Embrace parallelism and distributed system. And there are what? Even more reasons. So as we will what? See in the next slide. See what are those reasons? So let me what? Start with one more. See, we are continuing our discussion on motivations, guys. Let's look at what few more points I have what included in this slide. What is the first one? Better reliability. Guys, when you have many machines, many nodes, the chance of all of them falling at once is very low, right? Would you agree my point? Even if one machine goes down, others can take over its work. So this is called as fault tolerance. Maybe you have heard about this keyword previously. This is called as fault tolerance, is it? However, a word of caution here. So we must be careful about data integrity and maintaining a consistent state of resources across concurrent access. So this is a big challenge in distributed system, and we will talk about it little later, guys. I'm going to give you in detail explanation on each and everything in upcoming slides. No need to worry now. So another key motivation is incremental scalability. This is very, very important, man. Incremental scalability. Guys, you can add more nodes to the cluster to scale up your system as your needs grow. So you just imagine, guys. So initially, we have started with Zomato. Okay, we have started with what? Zometa. Okay, Zometa or Zomato. Okay, whatever it is. We have started with Zometa for a what? Minimum number of people. Okay, on that time, they have invested on what? 20 computers. You just imagine. I'm just imagining, that's it. So once the business grows, they have started what? Including more number of systems, right? Or they have started with what? Upgrading their system, scaling their system. This is called as incremental scalability. Are you getting my point, guys? You can just add another one to your existing cluster. That is called as scalability. And finally, these systems allow us to afford computing closer to user for scalability and better resource usage. So this is the concept behind edge computing concept. Okay, imagine, guys, a server handling requests from users all over the world. I'm repeating, guys, a server handling requests from users all over the world. By putting smaller computing resources or by putting edge servers closer to the users, we can reduce latency and improve performance. So this is a very popular model nowadays we are all using. And also this is one of the booming technology nowadays. Correct, no? Are you all getting my point, guys? See, here you can see the images. So this is illustrating these points with examples like Netflix. So they use a distributed network of content caching servers, so which are essentially edge servers. Understanding my point, guys? Why they are using? To deliver content faster to users. So this massively scalable architecture is built on hundreds of distributed microservice and hardware. So that is integrated with the another vendors actually. So this is a perfect real world example of distributed system in action. Okay, so let us take few more examples here. You can take a few more examples here. See, time for a little interactive thought exercise. So this slides presents 4 examples and ask us to think about the motivation for using parallel and distributed computing in each case. Let's go through them one by one. Okay, what is the first one I have taken here? The very first one I have taken here is airline scheduling. Okay, this is, I have used airline scheduling. Okay, think about the complexity here. What are the complexity in airline scheduling, guys? Can anyone answer? What is the complexity we are going to face in airline scheduling? Guys, you have to schedule thousands of flights, taking into account things like plane availability, crew rest time, airport gate availability, and also along with that, we have to think about weather forecasting also, weather conditions. So this is a massive optimization problem with too many variables for a single computer to handle in a reasonable amount of time. Correct, no? So the motivation here is performance and scale. So we need to solve a very complex problem fastly. That is the first example I've taken here. And what is the second example I've taken here? See, look at the second one. Summary statistics of historic sales data of a retailer. Okay, sales data of a retailer. Correct. Now, that is also one of the example. A large retailer can have terabytes or even petabytes of sales data. Calculating summary statistics like total sales by regions or average basket size, and involves what? Processing all this data. The motivation is clear: to handle huge amount of data in a what? Reasonable amount of time. We would use distributed system to partition the data, and process is in parallel. Correct, no? And third one is about web crawler. So we can take the example of web crawler also. A web crawler's job is to what? Index the entire web. Okay, the web is constantly changing and has massive number of pages. The motivation here is both scale and inherently distribute the nature of problem. The pages are hosted on different servers all over the world. A web crawler has to be what? Distributed system to be able to access and process all that information efficiently. And finally, we have weather forecasting. So one more challenge with respect to what? Weather forecasting, guys. This is one of the what? The biggest challenging domain actually. This is one of the what? Prime example of performance driven need. Weather forecasting involves solving complex equations on a massive amount of data from sensors, satellites, and models. The calculation must be what? Completed very quickly to be useful. So the motivation is sheer computational power to solve a large, complex, and time-sensitive problem. Okay. So other than this, so we have this examples, guys. Other than whatever the example I've taken, other than this, you have these 4 examples. So these 4 examples you have to go through one by one. Okay. Now look at here, guys. Look at the what? Distributed network of content caching server. See here, I'm explaining you. I was talking about 8 server, right? So nowadays we are all using 8 server, which is very close to each and every cloud actually. This is our original server. See here we have one 8 server. So in this region we have one 8 server. So here also 8 server, 8 server, 8 server. So this will always save the time. Okay. Now look at here. This is the example I have taken to explain on you guys. Airline scheduling, statistic, web crawler, and weather forecasting. Everything is done now. Now we are moving forward and we are talking about techniques for high data processing. What are the different techniques we are going to use for high data processing? Look at here, guys. So first one is cloud cluster computing. We all know the definition of cluster computing. So this is very common approach in big data. A cluster is a collection of computers which can be homogeneous or heterogeneous using commodity computers. Definitions are given here. You just go through this. So even I have mentioned usage also. And next we have MPP concept, massively parallel processing system. So these are typically proprietary distributed shared memory machines with an integrated storage. That definition also given here. They are often used in traditional data warehouse and data processing appliances. For example, we have used it in EMC Greenplum. So which is a what? Version of PostgreSQL running on a what? MPP system. Okay. And these systems are highly optimized for specific workload, but can be more expensive than the cluster. That you should understand. And finally, we have HPC, high performance computing, or we can call it a supercomputer. Guys, these systems are known for offering high performance and scalability by using in-memory computing. Okay, so HPC is typically used to develop specialty and custom scientific applications for research. where the result is more valuable than the cost. Here we are not going to give a value to the cost. We are going to value the result. In that situation, we can use this HPC. Understanding my point, guys? So think of a complex simulations in physics, complex simulations in chemistry, climate modeling. So everywhere, so we are going to use this HPC computers. Okay, so while all these techniques are about parallel and distributed processing, they differ in their cost, architecture, and typical use cases. Guys, cluster computing is most common and versatile for general purpose big data, while MPP and HPC are more specialized. Is this clear? So that's all about the very first portion of your course, guys. So just now I've completed with first 2 bullet points. So if you have any doubt on this, quickly ask me a question in chat box, or else we will move to the next point. Yeah, Netflix, you take the example of Netflix, Priyanka. See, I've taken 4 examples, right? Say I'm leaving you people to understand the Netflix and also reminding all 4 examples. Can't you do that, Priyanka? Because in previous session, I've taken the same example, Netflix example. You keep Netflix in your mind and talk about parallel programming and also distributed computing. Clear? Priyanka, I am not skipping that slide. I'm leaving you people to understand that. Okay, so I'm not getting any responses on chat box. All right, friends. So we have covered the first 2 items on our list. What parallel and distributed systems are and motivations behind them. Okay, so we have laid a solid foundation. Everyone will agree with my point? Yes or no? Everyone will agree with my point, guys. Now look at here. Now onwards, we are going deeper and understanding next big topic. So which is the what? Limit of parallelism. So this is a what? Fascinating and somewhat sobering topic, correct? No? So it teaches us that simply throwing more processors at a problem is not always the answer. So we'll explore some of the what fundamental laws and limitations that govern how much speed up we can actually get from parallel computing. Okay, so let's get into it, guys. So here, the very first slide, I'm explaining you on limits of parallelism. Guys, as we discussed, adding more processor to a system does not necessarily make it infinitely faster. The reason for this is a fundamental limitations. Okay, most parallel programs have both a sequential or a serial component and parallelized component. Okay, so think of parallel program like this, guys. So read data, let me write here, read data from a file. This is the first step. And second one is perform calculations on the data. And third one is write final result back to the file. Okay, these are the what 3 programs I have written, guys. Okay, Amdahl's law, so which we will discuss next, tells us that the effective speed up of a parallel program is limited by the fraction of the program that is serial. Correct? No? That is the concept of Amdahl's law that you have learned in B. No matter how fast you make the what parallel part, you are still constrained by the time it takes to run the sequential part. So this is a very important point, guys. You have to remember this. Okay. So, and it is one that often surprises people. So let's dive into Amdahl's law and see the math behind this limitations. Okay, so I'm taking Amdahl's law here. So this is the what super important concept. Even I am saying this is the what super important concept because one definite question you are going to get in your examination on top of this. So even you can see in your previous paper, you got one question on each question paper. Okay. So Amdahl's law gives us a what? Theoretical limit on the speed up so we can achieve with the parallel program. Okay, let's define a few terms here. What is the first term? I'm trying to what explain T of 1. This is the time it takes to complete a job using single processor. And what is the next one? T of n. This is the time it takes to complete the same job using n processor. Then the speed up is defined by using this two terms. What is speed up? Speed up is equal to speed up S of n equals to T of 1 divided by T of n. Ideally, for a perfectly parallelizable program, this speed up would be n. Remember this. Okay. Are you getting my point, guys? Now let's introduce the core assumption. Assume a fraction of the program. Assume a fraction of the program f. I'm considering small f as a what? Program. So this cannot be what? Parallelized and must be run sequentially. The remaining part, what is the remaining part? F is okay. So this is running serially. What is remaining part? That is 1 minus f, right? So 1 minus f can be parallelized here. So the time it takes on n processor is T of n. Correct, no? That is equals to T of n, is it? So that will be what? Sum of the time for the sequential part and the time for the parallel part both. So how do you calculate T of n, guys? T of n equals to T of n. Look at here, the formula. T of n equals to greater than not required here. T of n equals to f into T of 1 plus 1 minus f into T of 1 divided by n. So this is the time taken for parallel programming. This is the time taken for non-parallel programming, serial programming. Understanding my point, guys? Guys, the sequential part takes the same amount of time regardless of the what number of processors. But the parallel part gets faster by a factor of n. That you should remember. Now let's plug into the what? Our speed up formula. See, we have substituted the same into this speed up formula. See, what is T of n? T of n we have substituted here. See, look at the formula. T of 1 divided by T of n, right? The same thing I have substituted here. F into T of 1 plus 1 minus F into T of 1 by n. And finally, after what performing all calculations, what you are going to get, guys? S of n equals to S of n equals to, this is the simplification form, simplified form. S of n equals to 1 by f plus 1 minus f by n. This is the simple formula as a what? Profound implication. As the number of processors n approaches infinitely, the term 1 minus f by n goes to 0. This means that the maximum possible speed up is limited to 1 by f. Look at here, I have mentioned here clearly. So the speed up is limited by the sequential fraction of the code. So this is a huge realization, guys. No matter how many processor you throw at the problem, if even a small part is a sequential, your speed up will be limited. Okay, this is why Amdahl's law is so important. It gives us a theoretical upper bound on what is possible. Understanding my point, guys? So next, look at here. We have taken one example to explain the same. Look at the example we have taken here. Let's take a what practical example to see Amdahl's law in action. Suppose we have a program where 10% of the code is sequential. Look at here. 10% of the code is sequential. And that means, what is the meaning of this, guys? What is F now? F equals to 0.1. Since it is 10%, I have taken F is equal to 0.1 here. What about the remaining? Remaining 90% is what, guys? Remaining 90% is parallel, correct? No. Remaining 90% is parallel. So how many processors we have here? So we have 100 processors. 100 processors. Now they are asking us to calculate what is the effective speed up. Let's calculate the effective speed up using the formula we just derived. See, let me take the formula directly here, guys. S of n equals to 1 by f plus 1 minus f divided by n. So n is nothing but what here? N equals to 100. Number of processor equals to 100 here. So S of n equals to 1 by, what is f? F is equal to 0.1. I'm substituting directly here. Plus 1 minus 0.1 divided by 100. See, finally I'm getting 1 by 0.109 and approximately I'm getting 9.17. So even with 100 processors, the speed up is only about 9.17 times. See, we have 100 processors, but still this is what? The speed up is only about what? 9.17 times actually. Not 100 times, right? Not 100 times, is it? So this is because the 10% sequential part puts a hard limit on how fast the program can run. Guys, this example really drives home the main point of Amdahl's law. The sequential portion of your code is the bottleneck that prevents you from achieving a linear speed up with more processors. So this is why programmers and system architects spend so much of time trying to minimize that sequential fraction. Correct, no? But wait, guys, there are more to the story that just the sequential part. Let's look at some other limitations. What is the one more limitations here? Look at here, guys, everyone. See, Amdahl's law is great theoretical start, but in reality, there are other factors that limit speed up besides the sequential component. So one of the most significant is communicational delay. Correct? No. See, here I have mentioned here. One of the most is communicational delay. Guys, in distributed system, processors have to talk to each other to exchange data. I think everyone will agree with my point. Is this not going to take time, guys? Is this not going to take time? So let's look at the simple thought experiment. I'm taking the simple thought experiment here. Assume a processor can execute an instruction in 0.5 nanoseconds. This is what we are assuming initially. Assume the network delay for a message to travel one way is 10 microseconds. Okay, now let's calculate how many instructions a processor could have executed during that one message delay. See, here there is a message delay, right? So now look at here, guys. How do we calculate this? Number of instruction is equal to, this is how we are going to calculate, guys. I'm going to calculate separately. Number of instructions is equal to 10 microseconds divided by 0.5 nanoseconds per instructions. Nanosecond per instructions. Okay, what is this 10 microsecond means? So 10 into 10 to the power of minus 6 seconds, correct? No? Divided by 0.5 into 10 to the power of minus 9 seconds per instructions. Second per instruction. So what is the number of instruction now? Can anyone calculate? 10 to the power of minus 6, 10 to the power of minus 6 will get cancelled. you are going to get 10 to the power of minus 3 here, 10 to the power of minus 3 here, and this is 0.5, right? 0.5 means it will go 5 I'm taking means this is 2 times it is going. Hardly you are going to get 20,000 instructions, correct? No, 20,000 instructions. This is a massive number, right? Is this not massive number? See, during the time it takes to spend just one message, a processor could have performed 20,000 instructions. So this is why communication overhead is such a big deal in distributed computing. And it is not just communication delay. Okay, other overheads also reduce the speed up, such as context switching, scheduling, load balancing, input output operations. Correct? Now you can see here in this diagram. So in this diagram, you can see the blue line in the chart on the slide representing reality. Reality shows this effect. While Amdahl's law predict continuous increase in speed up, reality shows that after a certain point, adding more processor can actually decrease the speed up due to all these overheads. So hope everyone understood. Is it not interesting concept, guys? So this is the limitations of parallelism. Is this not interesting concept? Is this not interesting, guys? Can I get quick confirmation on chat box? Interesting. If it is interesting, see, this is definitely interesting theoretical concept. So this is what the limitations we are going to face in parallelism. Okay. And look at here, guys. Next slide, I'm explaining you about superlinear speed up. Friends, my dear friends, sometimes we might see a speed up that is greater than n, the number of processors. So this is called superlinear speed up. And it seems to defy Amdahl's law, but it has a very simple explanation. Okay, so this can happen because of the memory hierarchy. So specifically the use of caches memory. A single processor has a certain cache size. So let it call it as D. See, here I've mentioned everything. So I'm calling it as D. When we use n processor, the total cache size available to the program becomes n times D. Correct? No? So this larger total cache can dramatically increase the chance of cache hit. How many of them will agree with my point, guys? So this will dramatically increase cache hit. Finding data in the fast cache instead of slow main memory. As a result, partition a data parallel program across multiple processors can lead to a better cache hit rate, especially in what we call it as embracing parallel application. Here I clearly mentioned embracing parallel applications. Right now, where there is not much communication overhead. The speed up we observe is not just from the parallel computations, but also from the improved memory access performance. Of course, guys, so we have to be mindful of cache coherence overheads here. So which can add complexity. But the main takeaway is that superlinear speed up is possible here. And it is often a side effect of a better use of memory hierarchy. Now let's revisit Amdahl's law and its implications. Okay, now I'm revisiting Amdahl's law and also re-implications actually. Okay, look at here, guys, everyone. Amdahl's law can seem pretty discouraging, and this slide shows us why. Remember the implication we discussed earlier. So as the number of processors n becomes very large, the speed up S of n is approaches to 1 by f, that is a sequential fraction. Okay, sequential fraction f puts a hard upper limit on the speed up. Let's take an extreme example. Suppose 33% of the program is sequential. Of a program is sequential means what is f equals to? So f equals to 0.33 here. According to Amdahl's law, even if you had a billion of processor, the speed up would be less than, right? Yes or no, guys? Now look at here. 1 by 0.33 I'm taking here. So which is approximately equals to 3, right? So this is an incredibly poor return on your investment in hardware. So let's look at another example. Here. So to get speed up of 100 times with 256 cores, 100 times with 256 cores, what percentage of the algorithm must be perfectly parallelizable? Guys, for that we can use this formula. So 100 is less than equal to 1 by f plus 1 minus f by 256. Which means what we are getting at the end? We are solving for f here. We are solving for f, guys. So we find that f must be less than or equal to 0.0061, or what is the meaning of this, guys? The means that OPing 99.4% of the algorithm must be perfectly parallelizable. This is an incredibly high bar, correct? No, this is an incredibly high bar. So Amdahl's law is bad news because it tells us that even a small serial component can severely limit our speed up. So making it seems like parallel computing is not worth the effort. But this is the whole story, guys. There is a key assumptions in Amdahl's law that we need to challenge. So which we will do in the next slide. Okay, look at here. So here clearly I mentioned. So maybe we are missing something here. My dear friends, while Amdahl's law is mathematically sound, its core assumption might not always hold true in practice. The key assumption is that the total workload is fixed. So even as we increase the number of processors. But think about it, guys. Why do we add more processors? See, we don't just want to solve the same old problem faster, right? We want to solve new, larger, and more complex problems. As we get more resources, we can tackle bigger data sets or run more detailed simulations. So this is where Amdahl's law can underestimate the true speed up. Okay, the sequential part of the program does not necessarily increase with the number of resources, but the parallel part of the problem can grow much larger. For example, if we double our processors, we might double the size of the data set we can process. Okay, so the idea of a fixed workload is often too restrictive. So what if we assume a fixed workload per processor instead? So this leads us to another more optimistic law. So which we will be discussing in next coming slide. What is that? That law is called as Gustafson's basis law. Okay, you just look at here. This brings us to the Gustafson-Basis law. So which offers a different perspective on speed up. So it is a more realistic model for modern parallel computing where we use more processors to solve larger problem. Then what is the key idea here? The key idea is that as we add more processors, the size of the problem we are trying to solve also scale up. So let's start with our total workload. Okay, so what is total workload here? Total workload is represented by using W. So this is our total workload. We assume a fraction f is sequential as usual. So the workload is split into a sequential part, f into W, and a parallel part is 1 minus f into W. Now with n processors. Okay, the n processors, Gustafson's-Bars's law assumes that the parallel part of the workload scale ups by n. Then what is new larger workload? New larger workload W of n is equal to F into W plus n into 1 minus F into W. Correct, no? Guys, then what is S of n? So S of n equals to Wn divided by Wn divided by n, right? Sorry, W. This is S of n, is it? Initially, S of n equals to W of n divided by W. So then we are substituting. So S of n equals to F into, see, look at here, I'm substituting F into W plus n into 1 minus F into W, and the whole thing is divided by W. See, look at here, I have substituted. What is W equals to? W of n divided by W equals to this, I have substituted here. And finally, what I'm going to get, guys, finally, I'm going to get speed up of n equals to F plus 1 minus F into n. Correct, no? This is what I'm going to get at the end. See, the implication here is profound. Unlike Amdahl's law, the speed up is not limited by the sequential fraction. Sequential fraction F. So as n scales. So as you add more processors, you get a much better return on your investment because you are using them to solve a bigger problem. You are not using them to solve simple problem. Try to understand this. Guys, this law tells us to solve larger problem when you have more processors. So this is more accurate reflections of how we use modern big data system. Okay, suppose you are using big, see, the concept behind this is, suppose you people are using what big data tools to solve small amount of what data means, then how it is going to give a very good speed up. Are you getting my point, guys? Yes or no? When you add more servers to your Hadoop cluster, you are not just trying to run same job faster. You are often trying to what process a larger data set or run a more complex analysis. So this is very important perspective, especially in the context of big data. And we will revisit. So in our programming session, no need to worry now. You will understand. Suppose you are taking small amount of data, then what problem you are going to face. Suppose you are taking huge amount of data, then what differences you can see. Everything you are going to discuss in session number 5. Okay, so is this clear to everyone? So this concept is crystal clear to everyone? Yes or no? Quickly, I want each and everyone to respond, guys. Okay, fine. Guys, actually, now the time is 7:34. Okay, let me complete the syllabus first. So later on, we will discuss on that. So moving forward, guys, just now we have completed a deep dive into the limits of parallelism, and we have explored Amdahl's law and Gustafson's law, and this gives us a solid theoretical foundation. Now we are going to switch gears and get into very practical topic that is called as shared memory and message passing concept. Okay, this is a fundamental architectural choice that influences everything from system design to the way we write our program. Guys, understanding this will help you to appreciate the different kinds of parallel and distributed systems that are out there. Let's dive in, guys. Let's dive into the very first one. See, guys, you can see here. So I'm trying to explaining you memory access model initially. This slide introduces two different memory access model we use in parallel and distributed system. One is called as shared memory. Another one is called as distributed memory. Guys, let me start with the very first one, that is shared memory concept. Guys, in this model, multiple tasks on different processor can access a common address space. Look at here. Look at the diagram. So here we have a common address space. All the processors are trying to what? Access the same thing. This is conceptually easier for programmers. Guys, actually, one of your friend was asking about multi-core system, right? So this is multi-core. Okay, so you have a common shared processor here, shared memory here, but you have multiple processors. So we can call it as core 1, core 2, and core 3 also. So this is one processor. Under processor, you have core 1, core 2, and core 3. So here we have used shared memory concept. We have a single memory to what? Share the address. So this is conceptually easy for programmers. So think of it like a group of people working on a shared Google Doc. So everyone can read and write to the what same document, and they can see each other's changes instantly. So this is where this is one of the what very intuitive methodology, right? So the system handles the coordination of memory access for you people here. Guys, we see this in UMA and NUMA architecture. Correct? No. Same thing we have seen in the UMA and NUMA architecture, right? Same thing I'm explaining you here. What is the next one we have here? Next one we have here distributed system, distributed memory. Guys, in this model, multiple task. So even if they are executing a single program, or if they are accessing single data from separate and isolated address spaces. See, look at here. So for this, we have a separate memory here. Here also we have separate memory. Here also we have separate memory. Correct? No. So this processor can what request for this memory. This processor can request for this memory. So we are trying to execute, see, we are performing multiple tasks. We are executing single program, but accessing multiple data and also separate isolated address spaces. This is like having a group of people, each working on their own separate Word document. If they need to share information, they have explicitly sent a message or a file to each other. Correct? No? Otherwise, how they are going to what share the data? They have to share through what? Some messages or by using some email. So this is conceptually harder to program. Okay, you have to explicitly manage how and when data is moved between different virtual memories. Guys, you can see in this image. So both the images are giving clear picture on each and every concept actually. Communication between them must happen through an external mechanism like network. Okay, now let us start look at the implications for the architecture. Shared memory model. See, I've taken the shared memory model, and I'm talking more about implications for the architectures. Guys, so we are trying to elaborate it. Okay, by using architectural implications. In shared memory system, carefully listen to me. Many of them were asking questions on this. In shared memory system, all processors can access the physical memory or memories. Correct? No? A single logical address space. I'm repeating, a single logical address space for each processor is mapped onto this physical memory. The meaning of this is, from a programmer's perspective, they don't have to worry about where the data is located. They just refer to the memory address and system handles the rest. Correct? No. Guys, a single program is implemented as a collection of threads here. I was talking about threads. Okay, so here a single program is implemented as a collection of threads, and one or more of these threads can be scheduled to run on a processor because the memory is shared here. Correct? No? Different threads can easily communicate and share data by residing and writing to the same memory location. As we said before, this model is conceptually easier to program. Okay, guys, the analogy of the shared Google Doc still holds here. You don't have to explicitly send a message to your colleagues when you update a cell in a spreadsheet. They can just see the change. This simplicity is a major advantage of shared memory model. But this model has scalability limitations, guys. Scalability is very difficult here. As the number of processors grows, the shared bus or interconnect can become a major bottleneck, and that will lead into what contention and slowing down the system. So for truly large scale distributed system, we need to use different model. So which model is called as message passing? Okay, let's look at that in the next slide. So here, distributed memory and message passing I'm talking about now. Okay, so listen to me carefully now. So this slide is completely providing a very clear explanations of the differences between shared memory and distributed memory with message passing. Try to understand this. Guys, in distributed memory model, data has to be explicitly moved across different virtual memories. If a data item is in the virtual memory of task T1, I've clearly mentioned here. Okay, task T1. Okay, and task T2. See here, listen to me carefully. If a data item is in the virtual memory of task T1 and task 2 needs it. So T1 has to communicate it to T2. And T2 then has to make its own copy of the data in its own virtual memory. And this is an explicit communication step that programmer has to manage. Correct, no? So in contrast, in our shared memory concept, T1 simply writes the data to the shared memory location and task T2 can then read it directly. So this is because that memory location is a part of the logical address space. So that is shared between both the tasks. The communication is implicit here in case of what shared memory concept. The key takeaway here is that the distinction between explicit and implicit communication. Guys, distributed memory requires explicit memory. Let me write here. Explicit memory, sorry, not memory, message passing. Explicit message passing. So which can be harder to program, but is much more scalable because there is no single shared resource that can become a what bottleneck here. Understanding my point, guys? Okay, now let's dive deeper into message passing model in more detail in the next coming slide. See here, I'm talking about computing messages model for message passing. Okay, this slide outlines the computing model for message passing. So this is the model that dominates large-scale distributed system and is the foundation for many big data frameworks. Okay, guys, in this model, each data item must be located in one of the address space. There is no shared memory concept here. The data must be explicitly partitioned and placed on the different machines or nodes or in the network. So this is the key step. As the programmer has to decide how to distribute the data. That's it. All interaction between processors require explicit communications through the passing of messages. Already I've told you that, right? So passing of messages are very much required here. But see, I've told you, right? One more point also I've conveyed, right? So this makes it harder than the what shared memory model from a what programming perspective. However, as a note here, so look at the note here. So it is possible to create a shared memory abstractions on top of a message passing system, but it adds another layer of complexity. Guys, the simplest form of message passing involves a sender and receiver. So it will be having two things. One is sender, another one is receiver. The sender has the data and wants to send it, while the receiver needs to access the data. Okay, they must cooperate for this data exchange to happen. Okay, and the distributed memory model, while more complex to program, is far more scalable and resilient. So which is why it is the foundation of almost all modern big data system. Okay, now see, look at here. I'm talking about communication model for message passing here. Now look at the what specifies of how processes communicate in a message passing model. Guys, as we discussed, processors operate within their own private address spaces. Okay, to communicate, they send and receive messages. Okay, look at the first one, send. A send operation specifies the recipient and the buffer containing the data to be transmitted. And message identifier or tag we are going to use here. Then what about receive? A receive specifies, the receive operation specifies the buffer where the data will be stored and an optional message identifier. Okay, the key thing to remember is that sending and receiving messages is the only way to exchange data between processors in this model. Understanding my point, guys? See, look at the diagram here. The diagram on the slide so gives a what simple example. A process 1, okay, sends its local variable x as a message here. Process 2 receives the message and stores it as its local variable. So these values are the same, but they are completely separate memory spaces. So here we have a separate memory space and here we have what separate memory space. So this model, while more complex for the programmer, is what allows for the what creation of truly massive, scalable and resilient distributed systems. Okay, so now look at here. So look at the what distributed memory model implications for the architecture. I will quickly go through this. Guys, what does this message passing model mean for the architecture of the system? A distributed memory model is typically implemented in a distributed system. So which is a collection of standalone systems are connected in a network. A single task run as a collection of processors. A single task run as a collection of processors. And one or more of these processors are scheduled on each system or a node. Guys, the data exchange happen exclusively via messages sent over the network. Okay, since this is a what more complex model for programmers to deal with, there is often a distributed operating system or middleware layer to what hide some complexity. Understanding my point? See, that point is mentioned at the end. See what I'm trying to explaining you here, guys. What I'm trying to explaining you here. The data exchanges happen exclusively via what messages sent over the network. Since this is a what more complex model for programmer to deal with, there is often distributed operating system or middleware layer to hide some of the complexity. So think of frameworks like Hadoop and Spark. They provide abstraction that makes it easier for you to program with message passing. No need to think about message passing there. See, these tools are going to do the task very easily by its own. Understanding, guys? They provide abstraction that makes it easier for you all people, guys. The use of separate address spaces complicates the programming, but it also has a major advantage. So which we will discuss in the coming slide. Look at the advantages of using this. Guys, while the use of separate address spaces complicated programming, this complexity is often restricted to one or two phases of the program. The first phase is, okay, partition the input data. Look at here, I have mentioned here, partition the input data. So this is where we break up the large input data set and distribute it among the different machines. See, look at here. This data is partitioned and distributed among different processors. So this is crucial step because it helps to improve data locality. So then what do you mean by this data locality? You can ask me a question, right? What do you mean by data locality? Data locality means bringing the computation closer to the data. So when a process needs to access data, it's more likely to find it in its own local address space. So which is mapped to the memory of processor it is running on. So this is much faster than fetching data from the remote machines over the network, right? Because every data is distributed among what different systems. Okay, this is partitioning. And second step under the second phase under this is merging and collecting output data. Merging and collecting output data. So this is required if each task is producing output that need to be what combined to get a final answer. So we'll see what great example of this in our session of Hadoop MapReduce. So the complete concept of Hadoop MapReduce is depend on the partitioning and also merging concept. So here messages are communicated and outputs are merged to get a what final answer. This is the essence of what happens in many big data systems. Okay, there are different options for message passing, guys. So these are the different options for message passing. Now that we have understood message passing model, right? Now looking here. So we are talking about blocking and non-blocking options. Maybe you have learned this concept in your college days. Synchronization and also unsynchronization. What do you mean by blocking operations? We all know, right? Blocking operation is simple. The function call returns only after the operation is complete. For example, a blocking send operations won't return until the message has been sent. That is called as blocking. What do you mean by non-blocking? Guys, non-blocking is more complex. The function call returns immediately, even if the operation is not complete. You typically get a what handle back that you can use to check on the status of the operations later. You can see the same thing in a diagram. Blocking synchronous sends and corresponding receives. The sender, yes, look at here. The sender, yes, waits for the data transferred to be complete. And receiver R waits until the buffer is filled. Both tasks have to wait for each other. Understanding? The choice between these options is trade-off between simplicity of programming and performance. Okay, see guys, blocking synchronous calls are easiest to program, but they can lead to long waiting time. Non-blocking asynchronous calls are most complex to program, but offers the minimum waiting time and the highest performance. So that's why we have given important concept here. A note of caution is, so it is important to remember that a message can be received on the operating system buffer, but may not have been delivered to the applications buffer yet. So this is where distributed message ordering logic comes in. So which is a topic for more advanced discussion. Okay. And so next slide, see, look at here. Next slide, I'm explaining you about send and receive options. You all can observe here. This slide is providing great summary of different send and receive options for message passing. See here we have what? Blocking synchronous send, blocking synchronous send, and blocking asynchronous send, non-blocking synchronous send, non-blocking asynchronous send, and blocking synchronous receive, and non-blocking synchronous receive. So all the explanation I've given here, guys, you go one by one. I don't want you people to explain each and everything. I'm not going to do spoon feeding for you people. Okay, so this is completing the second part of the course actually. And we have left with the two more concepts, guys. So can you give me 24 minutes to complete this? So now the time is 7:55. Since time is over, so let me ask you guys. So if you are giving me 20 minutes more means I can complete the syllabus. So can you give me 20 minutes more, guys? Yeah, we will take 5 minutes break. So we can take 5 minutes break. Yeah, now the time is 7:56. So we can come back at 8:01. Is it okay for you all? I don't want to compromise, guys. I want to complete the entire syllabus. Otherwise, next class, we are going to face the same problem. Okay, I will give you 5 minutes of break, guys. So after 5 minutes, so we'll come back and we'll complete the syllabus. Okay, thank you all, guys. Okay, guys, shall we start the session? I'm back, guys. Ravi Kumar, it is there in Microsoft Team. You just go and find in Microsoft Team. All the recordings are available. Ravi Kumar. Okay, guys. Yes, great job, everyone. So we have now covered the first 4 points. Let me share the screen. So we have covered first 4 points on our list. So now we have discussed what parallel and distributed systems are, their motivation, the limits of parallelism, and the differences between shared memory and message passing. So now we are moving on to an equally important topic. Okay, so that is data access strategies, replications, partitions, and messaging. So this is going to play a crucial role in big data system tools actually. Okay, so I will explain you one by one, guys. So I will explain you one by one. So let us start with the very first one. Data access strategies. Guys, this is about how we organize and access data in these large scale systems. Understanding my point, guys? So we will be look at 3 key strategies here. What are the 3 key strategies? The very first one is replication, second one is partitions, and third one is messaging. Okay, so let us start with the very first one. What is the first one? So I'm not going to start with replication first. So instead of that, I'm going to start with partition first. Okay, so what do you mean by partitions? This is the first data access strategy, right? What is the partition? Guys, the strategy is simple in partition. We partitions the data typically equally across the different nodes of our distributed system. So it is like, so you have data, you are going to partitions this data into different pieces and you will distribute across different nodes. Understanding, guys? So imagine you have massive spreadsheet with millions of rows. Partition would mean splitting that spreadsheet into smaller files and putting each file on the different machine. That is called as partition. And this is the strategy. And this strategy has some great advantages. Guys, it works very well if your task or algorithm is data parallel. Correct, no? See, for example, if you need to calculate the average of a column, or each machine can work on its own partition simultaneously. It also works well when there is a locality of reference within a partition, meaning that the data a program needs to access is likely to be close together. Both will work out here, right? Understanding my point, guys? However, there are also cost concern. A major cost is the network access and merge cost. This is the major cost here. So if you need to calculate the grand total of the entire spreadsheet, so each machine has to compute its subtotal and then send it over the network to the central machine to be merged. Correct, no? And other concern is partition balancing is also one of the concern here. Okay, partition balancing. So which is going to ensure that each partition has a roughly equal amount of data and workload. Guys, we will be studying concept like shards and partitions in detail for systems like Hadoop and MongoDB. So when I'm going to teach you MongoDB concept, then I'm going to explain you this concept in detail. So this is very common strategy we are going to use in big data concept. Okay, So now let us jump into the second one. What is the second one? The second one is called as replication. So can anyone tell me what do you mean by replication? What is your understanding on replication? So replication is another key strategy for data access, right? What do you mean by replication? Copy of data, duplication. Very good. The same keyword we are using here. The same thing we are using in what? Big data also. Then what is the strategy here? The strategy here is to replicate all the data across nodes of the system. Correct? No. So instead of splitting the spreadsheet, we copy the entire spreadsheet onto multiple machines. We are not performing any partitions here. This strategy has a major cost. What is the major cost here? Higher storage space is required here. Because we are storing the entire worksheet, right? Entire worksheet we are storing means then definitely it will cost what? Storage. You are storing same data multiple times. You are replicating your data. However, the advantage are often worth it. With replication, all the data can be accessed from the local disk. That is the advantage, right? There is no runtime communication over the network. So this leads to high performance with parallel access. Try to understand this. This is the advantage. Correct? No. High performance with parallel access is one of the advantage of using this. And replication is also a key enable for failover across failover actually. If one machine goes down, you have an exact copy of the data on another machine, right? So your system can continue to operate. So this is the concept of what? High availability. High availability. Maybe you have heard about this. In cloud, high availability is one of the what? Availability. See, distributed data. What is the cloud actually, guys? Cloud is a part of your distributed data, right? Same thing. The main concern with implication is keeping the replicas in synchronization manner. So this is the challenge of consistency. That's it. Okay. So if one replica is updated, so how do you make sure all other replicas are also updated? That is one challenge we are going to face here. So we have a different consistency model to deal with this. So which we will study in depth for the system like MongoDB. That concept I'm going to explain you later. This is one challenge we are going to face with replication. Guys, replications and partitions are often used together in big data system to get the best of both worlds. Okay, now let us jump into the third strategy. What is the third strategy? Third strategy is dynamic communication. Correct, no? Guys, dynamic communication, or we can call it as messaging. Messaging. So this strategy is communicate at runtime only the data that is required. This is often used in situation where data is not partitions or replicated in advance, but is instead requested and transferred on the fly. So when you are requesting the data, on that time it is going to fly. The cost here can be high network cost. Correct? No. Every time it has to fly from one system to another system. So for that, what is required? Network is required. Network cost is very important here, especially for loosely coupled system. And if the data set to be exchanged is large, then definitely we are going to face a bigger issue here. However, the advantage is that communication cost can be minimal when only a small portions of the data is actually required by each node. For example, if a program on one machine needs just a single record from a database or another machine, so it can just request that one record. That's it. The concern with this strategy include need for high availability and performant network and the assumption that the data processing tasks are fairly independent. This is the concern. Okay, these three strategies, partitions, replication, and messaging, are the core techniques for managing data in our distributed environment. So I hope everyone understood these three concepts. Next slide. So we'll look at how we store this data. Look at here. Network storage. We are going to call it as network storage. Guys, this slide briefly introduces us the different ways to store data in a networked environment. So which is the key part of our data access strategies, correct? No? So when we talk about storage on a network, we often refer to two types. One is SAN, that is storage area network. And another one is NAS, that is network attached storage. What is this SAN, guys? So this provides raw access to data at the disk block level. So it is very fast and is often used for high performance databases. Correct, no? And what about NAS, guys? NAS is nothing but what? Network attached storage. So this provide file level access. So it is most common and user friendly way of sharing files over a network. Okay. So in the world of cloud computing, we also have storage as a service. Maybe you have heard about this. Storage as a service. Storage as a service. A great example of this is Amazon S3. So which provides a highly scalable and durable object storage service. So these cloud storage services abstract away the what? Physical detail of the storage and allow us to access data via a simple API. So we will cover these storage concept in more depth when we do an in-depth case study of Amazon storage service later in the course. So we have one program on this also, guys. On Amazon S3, we have one practical program. So then I'm going to give you more information on this. Okay. So that's all about the what? Fifth point. So we have what planned to discuss in today's session. Okay. So we have done with fifth point. So we have talked about parallel distributed computing, motivation, limits of parallelism, shared versus message passing, and different data access strategies. So now we are going to wrap up with our final topic, that is called as cluster computing. So this is very important topic because it is the most common and practical way of implementing a distributed system for big data system. Okay, so let's quickly dive into next slide. Cluster definition. What is cluster definition, guys? Can anyone give me the definition of cluster? Quickly. What is the definition of cluster, guys? So cluster is a type of distributed system and it is consisting of what? Collections of interconnected standalone computers that work together as a single integrated computing system. Am I right or wrong, guys? So think of a cluster as a what? Group of individual computers. So each with its own memory, each with its own CPU, operating system, and all tied together by a what? High speed network. So they are not a single machine. Try to understand this. They are not a single machine, but they act like one from a what? User's perspective. You go and search in Google, you will see the what? Picture of a cluster. It behaves like a single system in the view of what? Users, but it is not a single system. So can you give me an example on cluster, guys? Can anyone give me an example on cluster? What are the common examples? Including web and application server cluster, database server cluster, and cluster that run cloud services. Correct, no? All these are example for the clusters, is it? So look at the diagram. So this image is giving visual representation of a simple cluster. So with multiple computers connected by an interconnected network. This setup is basic building block for almost all modern big data architecture. Okay, so see here, look at the what objectives of this cluster. What are the objectives of the cluster? A cluster typically built for one of main two reasons. The first reason is high performance and second reason is high availability. Correct? No, I think everyone will agree with my point. So what is high performance? Guys, these are often referred to as a what? Compute cluster. The goal is to use the what collective power of all the computers in a cluster to solve a problem faster than a single computer could. For example, let me take the example of Hadoop cluster. So Hadoop cluster is also best example for this actually. Hadoop cluster uses this principle to run independent MapReduce jobs. MapReduce jobs on multiple nodes to process large amount of data in parallel. That is the best example for this compute cluster. And what is the second achievement? The second achievement is high availability. Already I've explained you about high availability, right? This is achieved by using this redundancy. By having multiple computers, you can ensure that if one fails, other can take over its work and the service remains available to the users. This is common use case for what? Web server cluster, database clusters. Guys, in Hadoop, so we also uses this principle by replicating data on multiple nodes for fault tolerance. Understanding my point, guys? Guys, an off-the-shelf or custom load balancer can be used to distribute the incoming workload across the nodes in the cluster, which is how these objectives are achieved in practice. Okay, so to answer the question on this slide, guys, this is very relevant for big data because most big data systems like Hadoop run on a cluster configurations to achieve both high performance and high availability. What is the question? How is this relevant for big data? So this is the question. Okay, so you can answer for that, and answer is given here. You can go to that later. Now, see, we are moving to the next slide. So cluster peer-to-peer computation. Guys, this slide introduces another way to classify distributed computing models based on the structure and interactions of the node. The two main models are client-server model and also peer-to-peer model. Okay, a cluster is often a good example of what, guys? A cluster is often a good example of peer-to-peer model. The meaning of this is each node is a peer. So it can perform core computations and acts as both a client and a server to other nodes. So this is different from the traditional client-server model. So however, a cluster can also have a hybrid structure. Understanding my point, guys? So this can also have hybrid structure. So there may be what special control nodes that allocate and manage work, thus having master-slave relationship. So we have a what? Master-slave relationship here. Okay. So the best example for this is Hadoop. Again, I'm giving you Hadoop as an example because in future we are learning more on Hadoop, right? That's why I'm giving you an example. I'm taking an example of Hadoop actually. So in Hadoop, so we are going to use two concepts. One concept is called as name node concept. Another one concept is called as data node concept. So these two concepts we are going to use in Hadoop. Guys, name node that manages the file system. And we have one more, resource manager. Resource manager. This resource manager that manages the jobs. And what this data node is going to do? Data node is going to what? Perform the computation task. So here, this name node and resource manager both are behaves like a master, and data nodes are going to behave like a slave here. So this relationship we have in Hadoop system actually. I will show you this guys little later. So once we are talking about Hadoop concept, I will explain you each and everything in detail. So now look at here, client server and peer-to-peer server. This difference, I think you might be knowing, right? So client server model, a server node performs a core computations or business logic here. The client nodes then send request to server for this computation. This is also known as request response model. This is also called as request response model. Correct? No? Because someone is going to send a request and someone is going to response to it. Okay. So example for this is email servers, network file servers. All these are an example for the client server computation. What about P2P? So this is also called as P2P model, right? P2P model, all nodes are considered as a peers here. Each and every node, they can perform core computations and may act as a client or act as a server for each other. They are equal. Okay, example for this is BitTorrent and multiplayer games, and some clusters are best example for this actually. Guys, the P2P model is very powerful for large scale decentralized system because it eliminates the single point of failure that a single server can be. So it is more resilient model. So this is more resilient model. That is P2P. Try to understand this. And what about cloud and cluster? Maybe you all know about cloud and cluster, right? A cloud uses data center as its infrastructure. Correct? No. Data center as its infrastructure. See, for example, we have AWS, Amazon Web Servers. This is having data centers in many regions. So you can choose where to deploy your services that you can do by yourself. And what is cluster? Cluster is the basic building block of the data center. Correct? No. It is a basic building block of the data center. So a data center is essentially structured as a collection of clusters. A cluster can be used in different ways in cloud environment. So see, what I'm going to say here is a data center is essentially structured as a collection of clusters, and it can host a multi-tenant services. So where multiple clients share the same cluster. So which is very cost effective, and it can be dedicated to individual clients and their services. Am I right or wrong, guys? So when we talk about big data in a cloud, so we are almost always talking about running our application on cluster within that data center. Remember this. Okay, I challenge you to draw a conceptual diagram to illustrate these cases, guys. So it will help you to understand this relationship better. Okay, now let's talk about motivations for using these clusters in more detail. See, these are the motivations. So we have listed one by one. The first motivation is the rate of obsolescence. Okay, obsolescence of computers is high. So this applies to everything from mainframes to supercomputer. Servers need to be replaced every 3 to 5 years. Then the solution to build a cluster of commodity workstations. So these are much cheaper and easier to replace. Remember this. Okay, you can incrementally add nodes to the cluster to meet increasing workloads. So instead of replacing the entire cluster, you can just add a new node. And the older nodes can operate at the lower speed. And this model is called as scale-out cluster. This is called as scale-out cluster. In a nutshell, clusters allow us to build powerful systems using cheaper off-the-shelf components, and they give us the flexibility to scale as needed. Okay, so we have another motivation here. This is the another motivation. You look at here, guys. Another motivation for using scale-out cluster with commodity workstation is that they are great for resilient software environment. So in this model, individual nodes may fail. Okay, but the middleware and softwares are designed to keep the computations running and services available for end users. So think about the backend systems of Google and backend system of Facebook. Okay, they use this model. A single server failure is a what? Non-event because the system is designed to handle it. The workload is simply shifted to other available servers. On the other hand, here I have mentioned, on the other hand, public cloud infrastructure is typically built as clusters of servers, so which have higher reliability than individual workstations. This allows for a what more stable foundation for the services they provide. So the choice of using workstation or more reliable servers as nodes in the cluster depends on the specific needs of the system and the level of resilience required. And then what are the typical components of the cluster? See, these are the typical components of the clusters, guys. You just go through this one by one. At the lowest level, we have individual cluster node. So this is individual cluster node. Each node consists of a processor. Look at here. Each node consists of a processor, memory, local storage, network data. And each node also runs its own operating system and owns other runtimes. And these individual nodes are all connected to a what? High-speed switching network. This is your high-speed switching network. The performance of this network is critical for the overall performance of the cluster, as it what enables communications between the node. Okay, on top of the individual nodes and the network, so we have cluster middleware. Look at here. So we have cluster middleware. So example for this is Hadoop. Already I've told you, right? So Hadoop is the best example for cluster middleware. The middleware is what ties all the individual nodes together and makes them act as a single system. So this provides the infrastructure for parallel programming environment like MapReduce, Spark. So it will allow us for what? Executions of the parallel applications. The middleware is what enables us to get all the benefits of cluster without having to manage each individual machine separately. Now look at here. Some more functions we have mentioned here. All the functions we have mentioned here. So single system images. So SSI, we are going to call it as SSI infrastructure. The goal is to make the entire cluster appear as a what single unified system to the user. So this is achieved by using single process space and single IPC space. Okay, single process space, single IPC space. So processors can communicate easily across nodes. Okay, we have single entry point or cluster IP. So you can access the entire cluster through one address. That is the advantage of using this. And you have single authentication. Okay, you have single authentication, a single memory and single input output space. Okay, you have single virtual machine. Okay, you have a what single management GUI. Guys, along with this, the middleware also provide high availability infrastructure. So it offers services for availability, redundancy, and fault tolerance. So it's responsible for recovery from failures and ensuring the system keeps running even if a node goes down. Okay, so this middleware is what makes it easy for us to work with cluster. It abstracts away a lot of the complexity of managing a distributed system. See, look at the example for this is Hadoop system. Hadoop system is the best example for this complete cluster concept. My dear friends, this is the perfect example of cluster. So we will hear a lot about Hadoop in this course, guys. I'm not going to explain more on this now. So in high level, in Hadoop, a big job is divided into many smaller tasks. So every task is either a map and reduce. Look at here, map and reduce. So these tasks are then assigned to a what set of nodes. So which form the cluster. Okay, Hadoop has special control nodes that manage all other nodes in the cluster. So they are responsible for resource management, setting up tasks, monitoring their progress, transferring data between nodes, and handling failover if a node goes down. Guys, Hadoop clients work with these control nodes to get the job done. Okay, so see, look at the images. So both the images are giving best example for this. So first one is showing Hadoop map reduce, and this is showing Hadoop cluster. So with the what job starting and being broken into maps here. So which is then combined at the what reduce space. Okay, Hadoop is fantastic real world example that brings together all the concepts we have discussed today. Okay, it is bringing up distributed computing, message passing, partitioning, use of cluster to achieve high performance and availability. Okay, so with this, so I'm going to complete today's session, guys. So this is the summarization of today's session. Guys, we have started with motivation and classification of parallel system, including Flynn's taxonomy, so which gives us a way to what categorize different architecture. And then we have explored computing limits of speed up. So we have discussed Amdahl's law, so Gustafson's law, so which gives us two different but equally important perspective on how performances scale with the number of processors. And we discussed the different models of communications, focusing on message passing, so which is the core of distributed systems. We then looked at the different ways we manage the data in a distributed environment, specifically how we are going to replicate the data, how we are going to partition the data with the help of big data storage and access. And finally, we dived into basics of cluster computing. And we have seen how a collection of individual machines can work together as a single powerful systems. So these are the foundational concept, and solid understanding of them is critical for everything we will do in this course, guys. So with that, so let's wrap up for the today's session. Okay, guys, next session, so we are going to discuss more on big data analytics and system. So we are starting with big data analytics and also system in next coming class, guys. Okay. Okay, so big data analytics means we will take all these foundation principles we have learned and see how they are applied in the real world to build powerful systems for big data. So remember, guys, the journey of 1,000 miles begins with the what single step. Okay, so we have taken many important steps today. So keep learning and keep questioning, and look forward to seeing you all in the what our next session. Sir, do we have any homework lab assignment for this week before next Sunday? No, I'm not giving you any homework problem. Okay, you just go through the recordings, guys, because I've covered lots and lot of theoretical concept, which is very much essential for your big data systems. Lab access is still not available. I have sent a mail to them. I'm keep on requesting them. So even from your end, you can send a request to the operational team, guys. I'm doing that job. I'm doing that job continuously. So can we get the slides for the next lecture prior to the session? Yes, I'm going to upload it, Joshi. So you can find that in session 2. Ravi Kumar, I'm repeating you. Recording is already available in Microsoft Team. You go to your Microsoft Team. So let me show you. You click on Microsoft Team. So in Microsoft Team, go to Files. So in Files, you have a separate folder. So it is opening now. Click on this recordings. So once you are clicking on this recording, you will get all the recordings. So this is on computer organization. Yes, the same way you're going to get for big data also. Okay. It is there. Guys, if you have any questions, so you can use your discussion forum. So in discussion forum, yes, I am going to give you the answer. Otherwise, my LF is going to give you the answer. Okay, so better I will talk to operational team to get an access to your lab, guys. So we are going to give you assignment 1 and quiz 1 also we are going to announce shortly. Okay, so you'll be having time, guys. I'm going to give you timeline. No need to worry about that. Otherwise, in your handout, you have all the times, all the dates and time. Everything is mentioned in the handouts. You go through that. So what will be the syllabus for mid-year exam? So will it be subjective or objective questions? No objective, only it is subjective. I have told you, right? I already have uploaded you the question paper. You just go through that. The same type of question paper you are going to get in future. And yes, I have told you, right? More case study kind of problem you are going to get in the examination. Okay, so whatever the theory concept you have understood, that you have to write in your examination. It is completely subjective. It is not descriptive. Not objective, sorry. It is descriptive. Okay. And sir, when do we need to schedule for EC1 and EC2? That is there in your handouts. You just go through the handouts. Date is mentioned clearly. After completion of 8 sessions. Okay. The meaning of that is after 8 weeks, you are going to get your EC2. That is your midterm examination. So EC1, you have 2 part there. One is quiz 1 and assignment 1. So we are going to release soon. Okay, so once you're getting your lab access, then we will decide what a day for that, and then we will finalize it. Okay, if you want, I will show you guys. I think it is not there in the system. So if anybody is having that copy means you can paste me, guys. The date is already clearly mentioned in the handouts. I think it is here. You go and download these handouts. In handouts, it is clearly mentioned. See, here it is clearly mentioned, right? See, for quiz, we are going to give 1 week of time. That is going to start from September 1 to 10. Okay. And assignment, see, I'm planning for 2 assignments. Okay. So for quiz also, I'm planning for 2 quizzes. So quiz 1 and quiz 2. So quiz 1, you are going to get before your midterm examination, even assignment 1, guys. So once your lab is ready, then I will start explaining you the laboratory programs. So I'm not going to wait for the syllabus to complete. I will start with the lab programs, and then I will give you the assignment problems. Okay, is it clear? Yes, thank you, Varprasan. So before your midterm, you'll be having quiz 1 and assignment 1. After your midterm, post midterm, we'll be having quiz 2 and also assignment 2. Is this clear? So maybe next class, I'm not going to cover with, yeah, next class means, yes, I'm taking extra class, right? So when you have told guys, so Saturday is okay for you all. So Saturday, I'm taking extra class from 6 to 8. First quiz will be 5% in this case. Yes, it is for 5 marks. So Saturday, 6 to 8 or 7 to 9, I'm taking extra class, guys. So be ready with that. So let me complete the third session concept in next coming extra class. And I will take one more extra class to complete the fourth session concept. So we have crossed 4 sessions, but still we have completed only 2 sessions concept. Yeah, definitely. I'm going to announce this in announcement, guys. So I'm going to announce this in announcement. It is from 6 to 8, 6 to 8 or 7 to 9. And next week, slides I'm going to upload in Tuxila, guys, and also I'm going to upload in Microsoft Team. Okay, so this week also I did the same thing, right? So before coming to the class, you just go through the slides because I'm explaining plenty of theory concepts. See, all theory concepts are essential for your big data. To understand big data, all theoretical concepts are essential. So that's why I'm explaining what each and everything in detail. Okay. That's all my end, guys. If you have any questions, you can put it on chat box. Otherwise, please give me one line feedback on today's session. So with that, we are going to close today's session. So please give me one line feedback on today's session. What is the time now? The time is almost 8:43. I asked you people to give 20 minutes. Thank you all, guys. So thank you for your valuable time. I know actually for you people, you're all working people. Thank you for your patience listening. See, I have 33 students. Still, I have 33 students on my class. So this is good move, guys. Yes, thank you, Tanya. Tanya, please go through the recordings. So each and every concepts are important in upcoming classes. Yes, very lengthy. I am not getting your point. Not showing to me. Why it is not showing to you, Ravi Kumar? Hmm? Yeah, somebody shared. Ravi Kumar, you can unmute and you can talk to me now. Ravi Kumar, you are there? So go to Big Data System. On Big Data System, you have files. Click on files. So under file, you have recordings. See here, session 1, session 2, session 3. All 3 recordings are available. So even it is showing date, right? August 10th, August 3rd, July 27th. Ravi Kumar, it is there. Now in Taxila, you will not get any recordings. So only on Taxila, you are going to get PPTs, not any recordings. So to get the recordings, you have to visit Microsoft Team. Seni. Thank you, Jyoti. So that is not prepared by me. Actually, that is prepared by one of our senior. So the means this will go to An Indian Niyogi. This PPT is prepared by one of the senior professor. The appreciation will go to him, Jyoti. Thank you. At least you are going through that PPTs now. Okay, guys, then no questions means we can wind up today's session. So goodbye for now. So yes, guys, next week I'm taking 2 sessions. So one is on Saturday and another one is on Sunday as regular. Okay. So till then, bye-bye, guys. See you on next session. So have a nice day. Good night, guys.